let's say I give you a function d of n, and it's equal to the natural log of n squared plus 4 minus the natural log of n squared minus 1. And your goal is just to find out whether this sequence is going to converge or diverge. And I could say, well, okay, from yesterday, we know that a sequence converges to L if the limit as n approaches infinity of a sub n is equal to L. Otherwise, it diverges. So I'll say, okay, a sub n is just the general term. I'm naming this function d sub n, but the general term of d sub n is still natural log of n squared plus 4 minus the natural log of n squared minus 1. So what I need to do is think about what happens as this approaches infinity. If you think about it in this format, guys, you just say, well, this is, when you put an infinity in, you have the natural log of infinity minus the natural log of infinity. That's infinity minus infinity. You might think it's 0. And if you did, you'd be right, darn it. But that would be the wrong way of thinking about it. So you say, well, what's the right way of thinking about it? Infinity minus infinity is not always 0. Sometimes it's infinity. So what you would need to do in this circumstance is, this is an indeterminate form. We use L'Hopital's rule to determine it. So I need a fraction out of this. You know, oh, fraction's going to be easy. Condense these logarithms down. This is equal to the limit as n approaches infinity of the natural log of n squared plus 4 over n squared minus 1. You see what we're going to do now? So I was saying we could use L'Hopital, and we could use L'Hopital. You'd have to use L'Hopital twice. I'd rather not. So what do you know about a limit going to infinity whenever the degree of the numerator and denominator is the same? Come on. If this is 1 times a billion squared plus 4 divided by 1 times a billion squared minus 1, that plus 4 and minus 1 become completely, utterly inconsequential. And so this just becomes n squared over n squared, which cancels out and gives you a 1. So the limit as this approaches infinity is going to be the natural log of 1. Natural log of 1 is 0. Gorgeousness. Oh, and actually I'm taking the limit when I'm doing that, so I'm going to scratch that out, guys. Sorry. This would equal the natural log of 1, which is 0. Thus, this series converges to 0. Main thing there is that it does converge. Okay. For the next one, I'll say, what if I have a sequence C of n that is equal to some number n divided by n plus n to the 1 over n? Now, here's where you could use some pretty simple logic and just say, well, I can see that the degree of the numerator is the same as the degree of the denominator. Anytime that's the case, the fraction of the leading coefficients is going to be the limiting value as n approaches infinity. This answer is going to be 1. If you can just see it in problems like this, that's fantastic. That's all you have to do. You say, this sequence converges to 1. Done. Now, what if you can't see that? Oh, that's where you show it. So I'll say this is the limit as n approaches infinity of n over, and I'm saying you do not have to show this part, guys. Algebraically, we could evaluate this limit. And the algebraic solution would be to go in and divide everything by the highest powered x. So I'm going to divide everything by n. And so now I can see that this is going to give me the limit as n approaches infinity. Numerator is 1. Denominator is 1 plus, and I'd say, I know that this numerator is 1 over n. My denominator is 1. Okay, 1 is going to be larger than 1 over n. So I could say this term is going to be equal to 1 over n to the 1 minus 1 over n power. Whenever you have terms in the numerator and denominator, you say, where's the larger term at? In the denominator of that term. Subtract your exponents, 1 minus 1 over n. Which you could call n minus 1 over n if you liked for that exponent. But now, the point here is, I know 1, keep in mind, 1 is larger than 1 over n. This 1 over n is essentially 0 because its n is going to infinity. So this becomes 1 divided by 1 plus 1 over infinity to the first power. That term is 0, 1, 1. This answer is 1. The next one. Now, a series, so again, C sub n converges, and it converges to 1. The main thing we're looking for is that convergent or divergent.
So what we're doing here, is this just like an analytical tool for a series?
Yeah. Well, this section is actually kind of laying the groundwork for later sections in chapter 10 too. So all this thinking, that's just approaching a value of 1. And it's extremely important that you can just see it and not have to show the algebra. But if you need to show the algebra, that's fine. But I'd like you to just be able to look at this and say, well, if n's going to infinity, that term's irrelevant because it's infinity to the 1 over infinity power. So I'm just going to have this term over that. It's the exact same power, exact same coefficient. This answer is 1. Okay. Now, when I look at another one, this one has going to be a limit that does not exist, which means it's going to diverge. A divergent limit either means it's going to negative infinity, infinity, or that it doesn't converge simply to one number. So a convergent limit must converge to some number L. That was our definition. Must converge to some this number. In this case, the number L is 0. In this case, it's 1. Notice why this one would be divergent. I'll say B sub n is a sequence formula with negative 1 to the n times n cubed plus 2 to the negative n over 3n cubed plus 4 to the negative n. In a problem like this, it's important that you see what's there to kind of confuse you and what's there that you need. So when I'm looking at this problem, guys, I completely, utterly ignore this term and this term. Do you see why? It's a negative exponent. So I know that this is going to be 1 over 2 to the infinity power. That's not going to contribute anything when I add. Now, if I was multiplying it, I'd have to worry about it. But when I'm adding a number that's essentially 0, who cares? This is plus 1 over 4 to the infinite power. Again, who cares? So I could just say this function is only going to be dictated by these first terms. And now I'm thinking, okay, it's a polynomial function. if I ignore this term from right now, what would you say the limit of this function as n approaches infinity is? 1/3. So what's that going to do?
Negative.
Ah, that's what I needed you to see. It just depends. Is infinity, and we don't know, is infinity an even or an odd number? Who knows? So if infinity is an odd number, this is going to be negative 1/3. If infinity is an even number, it's positive 1/3. So since the limit of b sub n could be positive or negative 1/3, no limit exists, which means this does not converge to any one number L. So I'll say b sub n is divergent. In order to be convergent, the definition of that is that the terms of the sequence approach one number. Okay. Save the best for last. Out of this section. This is the best problem out of that first section. If I give you d sub n is equal to n squared times the group, the cube root of n cubed minus 1 minus n. So you can't use any just logic in solving this one. So when I say logic, this one's 1 because same power, same coefficients. That's using logic to solve it. Logic doesn't work on this one because you say, well, why not? You have the infinity squared times, this is understood to be infinity to the first power, technically the cube root of infinity cubed, infinity to the first, minus infinity to the first. So I have infinity squared times 0. Well, what's infinity times 0? It could be infinity, it could be 0, it could be any number in between. We don't know. So I say, if it's an indeterminate form, what do we use to determine it? L'Hopital. What do you have to have in order to use L'Hopital? Fraction. So I would try this. I'd say, well, okay, d sub n is equal to this cube root of n cubed minus 1 minus n. I could say divided by n to the negative 2 power. That's equivalent. So now my goal would be to try to find the limit of this term as n approaches infinity. And so I'll come down here and say, well, I'm trying to find the limit as n approaches infinity of, because I know I'm going to need to take the derivative, I'm going to go ahead and write this group to the 1/3 power, same thing. I have that in there. And now, L'Hopital's rule will say, okay, take this limit and apply it to the derivative of the numerator over the derivative of the denominator. When I take the derivative of the numerator, I need to remember chain rule in this first term, guys. I'd have 1/3 times the group n cubed minus 1 to the negative 2/3 power times the derivative of what's inside, 3n squared. That's the full derivative of the first term. Then I'd say derivative of the second term minus 1 over derivative of the denominator, negative 2n to the negative 3 power. So as I try to work with this, I would say, okay, I'm going to algebraically simplify what I've just done. When I algebraically simplify, what I'm going to do from this step to the next, I'm going to try to get rid of all negative exponents in this group. So I'm going to say, in that numerator, what if I multiply by n cubed minus 1 to the 2/3? And what if I also multiplied by n to the third? That's going to get rid of all negative exponents in your problem. It's going to make it look nicer. It still may not work, but hey, that's okay. So when I do this, guys, I can say, okay, my numerator, if I distribute this to both terms in the numerator, this first term in the numerator is going to be 1/3 times 3, so that's going to give me 1. This term would cancel with this term, and I would have n cubed times n squared is going to be n to the 5th. That certainly simplified down the first term. Now, unfortunately, it's simplified the first term, but it's made the second term messy because it's going to have all of this in that second term being subtracted. So I'll say minus, and I prefer to write the n cubed first, times the group n cubed minus 1 to the 2/3. Okay, in my denominator, this n cubed cancels out the n to the negative 3, so I'll have negative 2 times the group n cubed minus 1 to the 2/3. Okay, so now, I did simplify algebraically. I promise you we're in better shape now than we were here. Still don't like it. So if I think, okay, can I take the limit at this point? Well, this would be infinity to the 5th. Now, technically, this is still minus, and if you look at this, I'm hoping you're seeing, well, you have infinity to the 5th there as well, because this is n cubed raised to the 2/3 power, so that's really like n squared. N squared times n cubed is n to the 5th. So this is like infinity to the 5th minus infinity to the 5th minus some very small nominal term, divided by, so it's my numerator is 0, my denominator is going to be negative 2 times infinity to the 2nd power. So I can say, well, okay, it seems like it's 0, but am I sure of that? I'm not sure. It just depends what my numerator is. So this didn't lead anywhere. Sometimes L'Hopital does not, and I haven't done anything wrong. I just need to show you, sometimes L'Hopital doesn't help. So we're like, okay, try something different. Here's my second try, guys. And as you work, this is the kind of the frustrating thing about this class. There's not a single solitary thing wrong here. This is the legitimate first step. It's just didn't help in this situation. So you say, okay, what do I do instead? Here's what I would suggest. If L'Hopital ends up not simplifying, and it's pretty easy to see if L'Hopital is simple. We started with this. Is this simpler or more complicated? I say it's more complicated. So after one application of L'Hopital and even trying to algebraically simplify, if it looks more complicated than the original, stop and say, try to algebraically manipulate it. The algebraic manipulation I'm going to try here. What if I ask you to factor an n out of this group and pull it out and call this n squared on the outside here? So if I factor this term, already an n there. Could I factor an n out of this cube root? So it had to be an n cubed on the inside. So what I'm going to do is I know that the cube root of n cubed minus 1, that's going to equal the cube root of n cubed times 1 minus 1 over n cubed. Right? And then I can say, well, the cube root of n cubed can then come out as a 1. Or sorry, can come out as an n. So I'll say this group is going to equal n cubed is going to be factored out. When it factors out of this group, I'll be left with the cube root of 1 minus 1 over n cubed inside of there. If I factor an n out of an n, I have my minus 1. Okay. Now, that one subtle maneuver is going to make things so much more beautiful. I'm going to go ahead and rewrite this now, just like I did before, and say this is 1 minus 1 over n cubed to the 1/3 power minus 1 in the numerator, and an n to the negative 3 in the denominator. At first, you might not think that this is any better than it was before. I promise you it is. Here's why. And here's how you can see that it is. Whenever you take the derivative of this term, it's going to be a constant. Or sorry, since it's a constant, it's going to be 0. Whenever you take the derivative of the first term, you're going to have to use the chain rule. And as part of that chain rule, you'll be taking the derivative of the inside. The derivative of the inside is going to contain the derivative of n to the negative 3, which is going to cancel with the derivative of n to the negative 3 in the denominator. It's going to make it beautiful. So, that's what I'm going to do. So I'll say, okay, this is, if I try to find the limit as n approaches infinity of this fraction, and I'll go ahead and say it's 1 minus n to the negative 3rd, all raised to the 1/3 minus 1, over n to the negative 3rd. L'Hopital says that this limit is equal to the limit as n approaches infinity. The derivative of a group to a power, we bring the power down in front, times the group, to the power minus 1, so negative 2/3, times the derivative of what was inside. That's going to give us the derivative of what's inside is the derivative of negative n to the negative 3. That negative 3 comes down in front. It's going to become positive 3, so times positive 3 n to the negative 4. My denominator is just negative 3 n to the negative 4. So I know that the 3n to the 4th will cancel with this 3n to the 4th, but I'll be left with a factor of negative 1 in the denominator. So this is going to equal, and I'll scrunch it in down here. Oh, this is not L'Hopital, so please don't put an h over the equal sign again. I'm not using L'Hopital, I'm just algebraically simplifying. You only show the h when you take the derivative of the numerator and denominator. This is just going to equal negative 1/3, or I'll say negative 1 over 3 times this group, 1 minus 1 over n cubed to the 2/3 power. And I went ahead and rewrote the n to the negative 3 as 1 over n cubed again. Now, this should be able to be evaluated. You can say, okay, if I let n go to infinity, this is going to equal my numerator, negative 1. My denominator is going to be 3 times the group, 1 minus 1 divided by infinity. That's 3 times 1 minus 0. Negative 1/3 is your solution. So you say, since d sub n has a limiting value L equal to negative 1/3, d sub n converges to negative 1/3. Okay. Section 10. Now, everything in section 10.1 that we just finished there, those are sequences. So we're just thinking of each term in there. What separates that from the next section, 10.2, is everything in this section is going to be an infinite series. And our goal is going to be finding sums of infinite series. So an infinite series is just defined mathematically as the following. Say an infinite series, S sub n is equal to the limit as n approaches infinity of the summation. Now, You can use any index you want. You can use an index I, R, Q, whatever. The book, unfortunately, uses a small n quite frequently. Please don't get the small n and the capital N confused, though. It's saying your index starts at 1 and goes up to this capital N, which is the limit as capital N approaches infinity, of a sub n. Well, so each term a sub n, if you're summing it like this, you just say, well, this is going to equal a of 1 plus whatever a of 2 is, plus whatever a of 3 is, plus all the way on out forever and ever. Now, what if I ask you to write the following in summation notation? Meaning with a summation sign. Summation notation just has a better ring. And several parts to this one. I'll say part A. What if I give you the series of numbers and ask you to define it? 1 plus 1/4 plus 1/9 plus 1/16 plus ... This is more of a pattern recognition than anything. You'd say, okay, I'm supposed to be able to write this as a series. Do you know, can you look at and see what's the common term a sub n? What's the general term a sub n here? What's happening from one term to the next to the next? And it might be helpful to say, well, this term's 1 over 1 squared. The next term is 1 over 2 squared. The next term, 1 over 3 squared, 1 over 4 squared. So, well, if this is n equals 1, n equals 2, n equals 3, n equals 4, every term is just 1 over n squared then. Yes, that's the a sub n. So I'll say, okay, we can see here that a sub n is equal to 1 over n squared. It's not enough just to say what a sub n is, though. So I'll say, well, the summation of my series, S sub n, would equal the limit as n approaches infinity. And I'd say, well, I would start at an n value of 1, go up to infinity, or capital N, and then I put my common term in there, the 1 over n squared. Okay so far? Yeah, go ahead.
For the summation notation, I always use I.
Yeah, well,
I think the book even uses that.
they will use I, they will use J, they will use N. It depends on the author. There's really no one thing. I is the old-time way that we used to, and when you say old-time, you're like, oh, are you insulting I? No, that's the most commonly, because I stands for index. But I don't want you to think that you always use an I. It's probably the most common, but by far, I'd say, when I say most common, probably 40% of the time you'll see an I. But you'll also see J quite frequently. You'll see K quite frequently. Also N. Probably I the most. Looking at another. And if the notations ever bother you there in a homework problem, I have no qualms with you replacing it with an I. I kind of like that. Okay, sorry. If I look at the next one here. So, I want to create a series off of this, and again, let me specify, because there's several different answers you could put for this. Let's say I want this to be a series where n, or I, starts at 1, goes to infinity, the limit as n approaches infinity. Yeah. So this would equal, how would you get the common term here? So n needs to start at 1, but you'd say, well, this first term is 1 over 3 squared, the second term is 1 over 4 squared, the third term is 1 over 5 squared, but I need n to start at 1. There you go. That's it. So you just say, well, if that needs to be a 3 and n needs to be 1, then say 1 plus 2 is 3, n plus 2. So you'd simply say 1 over n plus 2 quantity squared. Now, obviously, this also leads us to say, is there any difference in that series and just saying this is the limit as n approaches infinity of n equals 3 to infinity of 1 over n squared? Wouldn't that be so much easier? They're equivalent. So most of the time, our bases and the summations start at 1. There's nothing saying that they have to. You still have an infinite summation of terms from 3 to n here. So it doesn't really matter whether you start at 1 or start at 3. They're equivalent. Term by term, they're going to have every single same term in there. So I can say, doesn't matter. C. What if I give you 1 minus 1/3 plus 1/5 minus 1/7 plus ... That should be enough to see the pattern. So notice what difference your denominators has from one to the next. Denominator, understood denominator of 1, 3, 5, they're going in increments of 2. So automatically that makes me think 2 times n. It can't be just 2 times n though, because the first term is 1. So if I think, well, 2 times 1 would be 2, I need a 1 down there. So using the same logic you said just a minute ago, Susie, well, okay, then subtract 1 from it. You said add 2 to it later, just a minute ago. So how about I let that denominator, so I'm thinking the denominator 2n, I don't mean, what? Ooh, I started to put plus 1. I'm going to keep it plus 1. Just because I don't want to admit to a mistake. I can keep it as that. Okay, so if my denominator is 2n plus 1, and I want to make that work, what is my numerator going to be? My numerator's always 1 with the exception of that alternating sign. So I need to account for the alternating sign. It's just going to be -1 to a power. And before I worry about what power that is, I need to think about the implications of me choosing 2n plus 1 in the denominator. I would say, well, this is going to equal the summation in n, where this is the limit as capital N approaches infinity. What do I need my index to start at in order for 2n plus 1 to work? Not minus 2. 2 times what plus 1 is 1? 0. So I can just say, start at n equals 0, go up to infinity. And then I can say, term by term, this will work now. 2n plus 1, 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. 2 times 2 plus 1 is 5, so forth. Now, my numerator. I need the first term to be positive, the second term negative, third term positive. So the first term is going to be dictated by the 0th power. -1 to the 0 is 1. So I can say, hey, that'll work. Just -1 to the n. For my second term, n would be 1, which -1 to the first, -1. My third term, n would be 2. -1 squared, 1. 2 times 2 plus 1, 5. It's going to work for every term. Alternatively, I could have said, what if I want to start at 1? I would have had to make my denominator 2n minus 1, and this would have had to been -1 to the n plus 1 or n minus 1 power in order to accommodate for the correct order of signs. Okay. What about one last one of these? I'll say 125 over 9 plus 625 over 16 plus 3,125 over 25 plus 15,625 over 36 plus ... I want to say what summation formula would give me this. S sub n is going to equal the limit as n approaches infinity of the summation, and I'm not even going to put my starting point on the index there because we'll see. So if I think about my denominators, well, easy. 3 squared, 4 squared, 5 squared, 6 squared. My numerator, I'm saying, well, these are going to be powers of 5. Notice 5 to the third, 5 times 5 is 25 times 5 is 125. And if you don't see that they're powers straight off, all you have to do is divide one numerator from the preceding numerator. It's always going to be a factor of 5 greater than the one preceding it. So I know that this is 5 to the third, 5 to the fourth, 5 to the fifth, 5 to the sixth. So I could say the easiest format for this, and it's fine, you don't always have to start at 1. You can say, well, it'd be easier to start at 3. So I'll say, okay, I'll start my base at n equals 3, or I equals 3 if you prefer. And I'll go up to capital N for infinity. And I know that my base is just going to be n squared. Sorry, the denominator, not the base. The denominator is n squared. The numerator is going to be 5 to the n. Now, what if I said, write the equivalent expression, although you'll probably think this is easy now, hopefully. And I need to put my limit as n approaches infinity up front. What would have to change? If I want the base to start at 1, then simply... Yeah, you say, well, if you're subtracting 2 from the base, then you need to add 2 to the n within the term. So you'll say this is simply 5 to the n plus 2 over n plus 2 quantity squared. And that would be the same thing. Okay. Now, moving on down through here. The next thing I want to look at is called the divergence test. This is actually one that students love, but they misuse. Because it's so easy, they want to apply it to everything that they see. It has limited applications. So let me go into it first of all. Now, unfortunately, we're going to have about no less than 10 different tests for convergence or divergence by the time we get through this chapter. It gets a bit overwhelming. What I'm going to give you is a chart that gives you a listing of all the different types of tests and what the test can do, what the test can't do, and when to apply it. So I think it's a good summary chart. But this is our very first one, so you don't need a chart yet. Even if we get that far, I don't know. It depends. If I get through 10.3 today, yes. 10.3 will only do 4 tests. If the limit as n approaches infinity of a sub n is not equal to 0, then the summation from n equals 1 to infinity of a sub n diverges. Pretty simple. Now, does that make sense to you? Well, it should. Think about that. If you're going to add infinitely many terms that never go to zero, you're going to be adding infinitely many terms of some quantity. Infinity times some quantity is infinity. That can't happen. So all it's saying is that these terms better end up going to zero if they're ever to hope to have a summation. Now, here's the next part of this, though. If the limit as n approaches infinity of a sub n equals 0, this is what people tend to forget, then the summation from 1 to infinity, and it doesn't necessarily have to be, it could be any number a to infinity, so don't get hung up on the fact I'm starting at 1, may converge or diverge. So what it is, because the divergence test is such an easy test, students just say, oh, well, the limit as a sub n goes to infinity is 0, so then they'll automatically say it converges by the divergence test. That automatically, hopefully you think, well, that just doesn't sound right. Can you prove something converges by using the test for divergence? No. Test for divergence does not prove convergence. It only shows if something does diverge. So just because the limit is 0 does not mean it diverges. Sorry, does not mean it converges. Okay, now, an example. So using the test for divergence, I want you to show, I'm already going to tell you it diverges, but show that it diverges. Show that the summation from n equals 1 to infinity of n over the square root of n squared plus 1 diverges. So this should be a very quick and very brief proof. And I'm kind of even hard to call it a proof. All I would do is just go in and say, well, this is my a sub n term. All I have to do is find the limit as n approaches infinity of a sub n. Guys, can you see what this limit is without doing anything algebraically or L'Hopital? You're right. What's the degree of the numerator? 1. The understood degree of the denominator is also 1 because it's the square root of n squared. That's n to the first. Anytime the degree of the numerator and denominator is the same, you take the fraction of the leading coefficients. Your answer is 1. Now, what if this had been n over the square root of 2n squared plus 1? You'd say, well, the degree of the numerator and denominator is still the same. You'd be going to 1 over the square root of 2. 1 over the root of 2, 0.707 would be your limiting value. But in this case, the limiting value is 1. And so, automatically, I can say, since the limit as n approaches infinity of a sub n does not equal 0, we know the summation from n equals 1 to infinity of n over the root of n squared plus 1 diverges. Now, another case. So, with this one, this is where the divergence test would fail. And by fail, it's not helpful. What if I ask you to find the summation n equals 1 to infinity of 1 over n times n plus 1. So if you tried the divergence test, so I might ask you on a test, apply the test for divergence and see what it tells you. It'd be a very quick thing. You'd say, well, the test for divergence, the limit as n approaches infinity of 1 over n times n plus 3, you can see that that's going to be 0 since the degree of the denominator is greater than the numerator. But that just means, so I'll say, mathematical notation. That means therefore. Therefore, we know that this series, 1 over n times n plus 3, could converge or diverge. So the only time the test for divergence is helpful is when it's equal to some non-zero number. If it's equal to 0, doesn't mean it converges. It means it could converge. So now, my goal is to try to work with this. What I have up here, this is called a telescoping series. And they're going to always have a very neat and familiar solution process. So if I just started trying to think of this, it'd be pretty hopeless. Now, here's what I mean. If I just started plugging in numbers, when I plug in a 1, I get 1 over 1 times 4, 1/4. When I plug in a 2, I get 1 over 2 times 5, 1/10. When I plug in a 3, I get 1 over 3 times 6, 1/18. Plug in a 4, this will be my last one. 4 times 7, 28. So I can see why, the nth term of this sequence is going to get small and it will approach 0. The limiting value is 0. I can see that. But does it get small enough, quickly enough, to not have a sum, to have a sum? Or does it get small slowly enough to where, it's very small numbers, but a very small number times an infinite number of terms is still infinity? That's the problem. Well, it's not too bad to find out. What we do with a telescopic series is we break it down just like we did partial fractions. So I'll say, let's analyze 1 over n times n plus 3. We're going to say that that's equal to a over n plus b over n plus 3. So we know that 1 is going to equal a times n plus 3 plus b times n. And so then you could let n equal 0. You get 1 equals 3a. So a is 1/3. You could let n equal -3. And you get still 1 is equal to -3b. So that would give me b is -1/3. Those are going to be helpful now. So I'll say, okay, I have my value for a and I have my value for b. What I'm going to do is say, this summation n equals 1 to infinity of 1 over n times n plus 3. I'm going to factor a 1/3 out and I'll say that's equal to 1/3 times the summation n equals 1 to infinity. So I've accounted for the 1/3. It'd be a over n, which is now 1 over n. And then it would have been plus a -1/3 or minus 1/3. I've factored out the 1/3, so now it's just -1 over n plus 3. I didn't want to have to worry about that factor of 1/3, so it just came out. But this is the same thing. So now, I can say the sum of this, of the n terms, is going to equal 1/3 times, okay, let's plug in a 1. And you kind of have to be patient with yourself as you work these problems. They're not hard, but it takes a bit of time for you to see the pattern. This first one, I would get 1/1 minus 1/4. Don't try to simplify it. Plus my next one. And when I say don't try, that's not this problem in isolation. Every telescoping series problem like this, you'll leave it out generally like this because you'll need to see the pattern. So I'll say my next term is when 2, I'll get 1/2 minus 1/5 plus 1/3 minus 1/6 plus 1/4 minus 1/7. Do you see something that's going to happen now for every next term? I'll go ahead and put the next term plus 1/5 minus 1/8. What do I know about the first term in every successive group after the first 3? After the first 3, this first term is going to cancel out with a preceding term. That term is going to cancel out with a preceding term. If I keep on going, plus dot, 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 let's talk about the last 3 terms. I'd say, well, the last 3 terms, I know that this first term is going to be the third to last term. The last term is going to be 1/n. The second to last term, 1/n minus 1. The third to last, 1/n minus 2. So I'd say it'd be 1/n minus 2 minus 1/n minus 2 plus 3, be n plus 1, plus the second to last term, it'd be the n minus first term. So this is 1/n minus 1, whereas this one is 1/n minus 1 plus 3, be n plus 2. Plus my very last term. If I go all the way out to n, I just get the term that's in there. 1/n minus 1/n plus 3. Now, the reason I'm doing this is because we know in this process, the first 3 terms are not going to have anything to cancel them out. But then every other term after that can be canceled with a term preceding. So I can say that would include these. This 1/n minus 2, it would cancel out with the second term of the group right before it. So I can say, I know that's going to cancel, I know this is going to cancel, and I know this is going to cancel because of this same procedure. So I can say, well, okay, now, so S sub n is going to equal 1/3 times what's left over. Well, you're going to have the first 3 terms left, 1 plus 1/2 plus 1/3. And you're going to have the last term left in your last 3 evaluations. So that's going to be minus 1/n plus 1, minus 1/n plus 2, and minus 1/n plus 3. So the sum of this telescoping series, I can say, okay, I know that the limit as n approaches infinity of S sub n is just going to equal 1/3 times the group. Notice if I take the limit as n approaches infinity of this group, I'll get 1 plus 1/2. They could care less what n goes to. There's no n in them. But now, what happens to these 3 fractions as n approaches infinity? 1 over infinity plus 1, that's a 0. The next term, a 0. The last term, a 0. So I can say minus 0 minus 0 minus 0. This is going to give me 1/3 times 1 plus 1/2 plus 1/3. Get a common denominator, I guess, of 6. 6 over 6 plus 3 over 6 is 9 over 6 plus 2 over 6 is 11 over 6. 1/3 times 11 over 6, I'm getting 11 over 18. Final answer. See what I meant about this being completely, utterly different stuff? Y'all don't see me do. Yeah. Next thing I need to talk about, a geometric series. This is dealing with them too. A geometric series, guys, is where we have the summation of some terms in a series is equal to the sum from n equals 0 to infinity of some constant term starting point we call c times r to the nth power. And so whenever we start evaluating the terms of the series, you'd say, well, what would the first term of the series be? When n is 0, that r plays no factor. You just say it's c times 1. Plus, when n is 1, you'll have, well, c times r to the first. Then you'd have cr squared plus cr cubed, so forth. Now, I could say, for an example here, so if the beginning term was a 5 and r was equal to 1/2, we know s would equal, our first term would be 5 times 1. Our second term would be plus 5 times 1/2, 5 over 2. Our third term would be 5 times 1/2 squared, 5 over 4. Then you'd have 5 over 8, so forth. It's just that common multiple of 1/2 for every term after the first one. Okay, now, we need to find a way to sum a geometric series, an infinite geometric series. Now, this might be something that I do ask you to replicate later on a test, because I think it's important logic in order to be able to show how a geometric series formula, summation formula, comes into place. I could say, well, okay, the sum of n terms, and you can put as n approaches infinity, I'm not going to, the sum of n terms is going to equal c plus CR, this is the same thing I have up here, CR plus CR squared plus CR cubed plus dot 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 CR to the n power. If I'm going out in terms. And say, okay, now what happens if I say, I want you to multiply R times S of n? You'd say, well, okay, if I multiply R times S of n, it's going to give me C times R plus CR squared plus CR cubed plus CR to the fourth plus dot 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 CR to the n plus 1. And there is a method to this. So you're like, where's he going with this? Right now, I can say, what if I ask you to sum these two lines? On the left-hand side, you have S of n And actually, I said sum, I meant subtract. Sorry about that. S sub n minus R S sub n. What I'm going to do is I'll say, okay, what term would be an unlike term in through here? The only term that S sub n has that R times S sub n could not cancel is the very first term. The R times S sub n doesn't have just a C value. So I can say, well, I can see that there'd be a C left. Then I can also say every other term would cancel with the exception of the very last term here. So it's going to be a minus CR to the n plus 1. Now, if I'm wanting a formula for S sub n, then hey, how about we solve for S sub n on the left? I'll solve for it by factoring out an S sub n. When I do that, I get 1 minus R remaining. Now, need to solve for S sub n. It's going to equal the right-hand side divided by 1 minus R. The sum of any geometric series is whatever the first term of this series is, minus that first term times the common ratio to the n plus 1 power, divided by 1 minus the common ratio. Now, I can say perfectly fine for this. Typically, if we go in and say, this is adequate, I'm going to go in and factor out a C. Like that. And now, we know, because of the test for divergence, any series only has a chance of being convergent if the limit as of a sub n of that series is 0. So the only hope that a geometric series is convergent is if the nth term of this sequence as n approaches infinity is 0. So think logically with me about that. What would the common ratio have to be in order for the infinite term to go to 0? So, for example, could R be 2? Hopefully you're thinking, gosh, no. Because those numbers are just going to get larger and larger and larger. Could R be 1? No, because then every number is going to be the exact same thing as the first term. 5 plus 5 plus 5 plus 5 plus 5 plus 5. Infinite many times. It's 5 times. It's not going to converge. We need that infinite term to go to 0. So you must have your common ratio be some number in between -1 and 1. Because in that case, every single term is going to get smaller and smaller and smaller all the way down. So I'll say, we know S sub n converges only if the absolute value of R is less than 1. So you could have a positive common ratio, you could have a negative common ratio. But whatever it is, it has to have an absolute value less than 1 in order for each successive term to be getting smaller, not larger. We need them to get smaller. So now I'll say, as n approaches infinity, R to the n, or to the n plus 1, will approach 0. So, the limit as n approaches infinity of our geometric series formula, C times 1 minus R to the n plus 1 over 1 minus R, I can say, well, that's just going to give me this R value that's raised to the n plus 1 power, that's going off towards 0. Because any number less than 1 raised to an infinite power, it's going to go off towards 0. So I'll just get C times 1. I'll show 1 minus 0. Your denominator, that r is not raised to the n power, it stays. So it simplifies down nicely to just c over 1 minus r. That's the summation of any convergent geometric series. Okay. Now, let's use that formula to solve the following. Determine the summation of the first n terms for, I'll say 4 cubed over 5 cubed plus 4 to the 4th over 5 to the 4th plus 4 to the 5th over 5 to the 5th, and this series goes on forever. You'd say, well, okay, I'm assuming it's a geometric series since it's right below what I did for the geometric series. You'd say, okay, so the common ratio here, what's happening from one term to the next? Well, every single time you're multiplying your numerator by 4. This one is a power of 4 greater than the one before. This one's a power greater 4 more than the one before. You're multiplying your denominator by 5. The common ratio is 4/5. So r is 4/5. The first term c is 4 cubed over 5 cubed. So I would say the summation of n terms, I'd say, well, okay, it's the c value, 4 cubed over 5 cubed, divided by 1 minus r, 1 minus 4/5. And we should be able to simplify this without the use of the calculator. I'll say, get rid of the fractions in the problem by multiplying by 5 cubed over 5 cubed. That's going to give me 4 cubed in the numerator. My denominator is going to be 5 cubed. And then minus 4 times 5 squared. So my numerator, 4 cubed. 4 times 4 is 16 times 4 is 64. My denominator, 5 cubed, 125, minus 4 times 25 minus 100. So I'm going to get 64 over 25 down there. Final answer. Okay.
A lot simpler than the explanation.
Oh yeah.
I feel like I got lost in the explanation.
But the use of that makes sense though?
Yeah, it makes a lot more sense.
Okay. A lot of times when you start working problems, it makes more sense than just the theory behind them.
As long as you don't have a question telling us to explain the theory. On the
Oh,
test.
now,
Okay.
might I say, prove the sum of a geometric series
Please
is
don't.
this? I'm not.
Please don't.
No.
I don't like that. It wasn't fun, but we're still going.
You'll have future higher level math classes where you have to do stuff. I promise. I won't.
Make it bonus.
Beware.
Make it bonus. Then I'll learn it.
Yeah, this isn't that class.
Well, I did tons of stuff like that in Math Logic. I've never taken Math Logic.
Can you just explain how you got R and C real quick?
Sure, bud. Sure. So, up here, notice in my general geometric sum up here, Clint, C is just the first term. If you let n equal 0, then you have no R term in there. You'd say C is just the very, very first term of your sequence. Sorry, of your series. R is what's happening to every term thereafter. So what I did here, when I looked at this, the very first thing, the first term is this. So there's no doubt what C is. So you just say C is the first term. Okay. Now, R, you say, what am I multiplying to get to this term, to the next one, to the next one? I'm multiplying the numerator by 4. I'm multiplying the denominator by 5. I'm multiplying by the common ratio of 4/5. Okay. Now, what if I go ahead and set up a summation for you? What are you going to do for that, guys?
Toss it.
It's actually quite easy.
No, it's
Zero.
It's 1.
no solution, move on.
Yes! You're
That was
right!
a joke. but okay.
You're right. Why? Why is it no solution?
It's your time to shine, kid.
So, notice what I put up here in the theory section. I was saying this, and maybe I should have put "we know" right there. We know. So I said we know that the summation converges only if your R value is less than 1. So, and again, why? Because if R is greater than 1, that common ratio is only increasing the size of every term. If you're going to add infinitely many terms, they better be decreasing at the very least. So I can say, okay, is your R value bigger than 1? So in this problem, if I ask you, label C, label R. C is the first term of the series. What would C equal? I was afraid you'd say that. The very first term, you say plug a 0 in. You'd get pi over e to the 0 power is 1. C is equal to 1. You'd say R is equal to every other term after that first term is going to be multiplied by pi over e. Your second term is pi over e. Your third term is going to be pi over e squared. Then pi over e cubed. Pi over e to the 4th. R is pi over e. But because pi over e is greater than 1, pi is 3.14, e is 2.7182818282812828. We know that this is greater than 1. Therefore, the summation pi over e to the n does not exist. Or, I don't like that. The summation diverges. That's better. That's more the lingo we're using now. Okay, now for number 6, I want us to do the reciprocal. So I'll say n equals 0 to infinity of e over pi
Hey, I think C is 1.
to the n. Oh, what do you say? I can't say something.
I think C might be 1.
Oh. I can see you're right. And R would be
E over pi.
C.
No, not C, R.
So the summation of this series is going to equal the C value, which is 1, divided by 1 minus R, 1 minus E over pi. I'll simplify by multiplying by pi over pi. And I get pi over pi minus E. Piece of cake.
Now, why do you multiply by pi over pi again? Or
Just
how
to
do you
get
derive
rid of the
that?
fraction inside the fraction. I saw a pi in the denominator of the denominator, which I said, ooh, I don't like that.
Okay.
So just multiply by it. Now I know what you're thinking. This is too easy, John. You got to get started to harder problems. Okay, still a geometric series. Still something I think we should be able to manage quite easily, but it's going to look a lot harder. Notice I said it will look a lot harder. I want to find the summation of that series. What do you think would be a good technique? Whenever you have an integral problem that has a complicated fraction and you have two terms in the numerator, we can separate it up into two integrals, can't we? I suggest doing the same thing here. So right now, it's not a geometric series in and of itself altogether. But if I just say, well, it's equal to the summation of all of this over 8n minus that over, yes. So that's what I'll do.
And so what makes that geometric? as
Well,
compared to-
right now it's not geometric because you can say, is there some common ratio multiplying this whole group in there? It's not. But now my goal, Michael, is to break it apart and prove to you that it's two geometric individual sequences. Sorry, series.
So how would we know to do that though? Other than just it's in this section.
Well, it's going to be saying using the geometric series test. So you know the whole thing's not a geometric series. So you'd have to know to break it apart. It's frustrating. I know. I've tried to add that. I know. The first one I'll say is 3 times. Ooh. Do you see where I'm going to get this?
Wait.
And then the second one,
That tricky there.
that. So I had to write it as a geometric series. So I said, okay, well, stop stuttering, John. What's the common ratio in this first one? My numerator is always going to be multiplying by -2. My denominator is always going to be multiplying by 8. So I can say everything in that first set, 2 over 8 reduces down to -1/4. Well, -2 over 8 reduces. So that's -1/4 to the n times 3. So now if I ask you, what's the first term in this first sequence? A 3. What's your common ratio R? -1/4. Over here, what's your first term? An understood 1. What's your common ratio? 5/8. Can you find the sum of these two series individually? Yes. So can we find the sum of the original problem? Yes. So I would say this is going to equal C over 1 minus R. R is a -1/4, so I have 1 plus 1/4 down there. From that I'll be subtracting. Over here, your first term is 1. You'd subtract that by 1 minus 5/8. The first one I would multiply by 4 over 4. When I do that, I would get 12 over, this would be 4 plus 1, 12 over 5. My second one I would recommend multiplying by 8 over 8. When I did that, my numerator would be 8. My denominator would be 8 minus 5, 3. 12 over 5 minus 8 over 3, that's the same thing as, say, 36 over 15 minus 40 over 15. This summation is -4/15. Final answer. Okay, now, section 10.3.
Now, do we have enough time?
Oh, yes. Maybe not to finish. 10.3 is our beginning of the use of convergence tests. So, the first convergence test that we're going to look at is called the integral test. And you will see the integral test on your test because it's, even though I'm not a fan of it, it's one of the more important ones. Why am I not a fan of it? Because the whole reason you sum a series is because usually the function that you're looking at is not integrable. So does it really make sense to use the integral test to determine if a series converges or diverges if the reason that you're using the series in the first place is because it was an integral? No. Hopefully you follow that. You're like, no, it doesn't make sense. So I'm not a fan of the integral test myself. A lot of people use it quite frequently, though. I've never really understood why. It's one of my least favorite. But I shouldn't have biased you against it. You might look at it and go, oh, that's wonderful, John. What the integral test says is that if f, so f of x being a function, I don't want to necessarily mean f has to be a function of x. So f is just some function. So if f is positive, decreasing, and continuous, then that's supposed to be not an S. Then S equals the summation from n equals 1 to infinity of f as a function of n. So then this summation, which is it's going to converge or diverge if the integral from m to infinity of f of x dx converges or diverges. For some positive value of m. I got too carried away with my humps into m. Now, hopefully this you're following it. I know it's kind of hard to follow. What I'm saying is that if I can find some answer to an integral, then that answer converges. So any non-infinity or non-existent answer is a convergent answer. If the integral converges, then the sum of the series that are just points on the integral also converge. If the integral diverges, then your summation diverges. It's just saying that whatever the decision is on the integral will be the decision on the summation. So I can say, okay, use an example to try to make it clear-cut. And I would specifically tell you which integral test to use. That's something that I think you'll appreciate later on, because once we get 10 integral tests thrown at you and you just look at a problem and it says, show if it converges or diverges, you're like, how? Which way? You won't have to wonder that in this class. You will know. I will say, use the integral test, use the limit comparison test, use the p-series test, you will know. We're going to have used the integral test, that's integral test, not it. Use it to determine if the summation from n equals 1 to infinity of n e to the negative n squared converges or diverges. Okay. So here's the thing, guys. You can't just go directly into it and say, okay, I want to integrate n e to the negative x squared dx. And if that has an answer, then this has an answer. If it were only that easy, things would be a lot nicer. Because in order to use the integral test, you must first show that the integral test applies to the problem. So what I have to show first of all is that, can I show that f of x is positive, decreasing, and continuous? So I'll say, so f of x, the function that this summation would be a part of, would be x e to the negative x squared. Now, I can handle the positive and the continuous part extremely easily. Here's why. We know that y equals x has a graph looking something like that. E to the negative x, it's just an exponential function turned in the opposite direction. The fact that you're squaring the exponent just is going to make it go more extreme in each case. So y equals e to the negative x squared, going to look like this. So I'll say, okay. Now, what do I know about each of these? This function is always continuous. So I would say continuity is assured since it is the product of two continuous functions. That would sound nice and fancy. The continuity of f of x is assured since both x and e to the negative x squared are both continuous functions. The product of any two continuous functions is a continuous function. Would you have to write that? No. Now, but you could. Now, continuity assured. How about the fact that it is positive? You say, well, I know that y equals x is positive for any value of x after 0. E to the negative x squared, any exponential function is always a positive number unless you have a negative out in front of it, flipping about the x-axis. So I can say the exponential function always positive. X is always positive for any x value to the right of 0. Well, my function, I'm only concerned about values above 1. So I can say clearly f of x will be positive on x equals 0 to infinity. Because it's the product of two positive functions. A positive times a positive is a positive, not positive. Now, the thing is, I can't use this same simple logic to show that it's decreasing. Now, if this function were decreasing and this function were decreasing, then clearly the product of two decreasing functions is a decreasing function. But I have one is decreasing, one is increasing. I can't say the product of an increasing and a decreasing function is decreasing. I don't know that to be true. Now, if I use better logic, I think e to the negative x squared is decreasing more sharply than y equals x is increasing. Because even down here where it starts to get really asymptotically small, that fraction is reducing by proportion so small that it's going to knock the y value down from the other. So I'm pretty sure it's decreasing. What method do we have to assure a function is decreasing? From Calc 1, a function is decreasing when its derivative is negative. Okay? Why? Negative means the slopes of the tangent lines are always negative, thus the function is decreasing. So that's what I have to do. I'll say, show f of x is decreasing and hopefully on the interval that we're interested in, which is from 1 to infinity. So I'll try. Well, f prime of x, I look at this and I want to use the product rule. I'll say derivative of the first is 1 times the second, e to the negative x squared, plus the first times the derivative of the second. Derivative of any exponential function is that exponential function times the derivative of its exponent. So I can say, well, that's f prime of x. I could say this is going to give me e to the negative x squared. And then I would have minus 2x squared e to the negative x squared. Okay. So if I want to use the first derivative test to find out when this function is increasing, decreasing, hopefully you remember it's helpful to find out the critical points first of all. That's where it's equal to 0. And then I'll set up test intervals to find out where it's negative. So I'll say, well, okay, find out when f prime of x is equal to 0. E to the negative x squared minus 2x squared e to the negative x squared. What I would do here, guys, is to make this easier to work with, factor out that e to the negative x squared. When you do, you're left with 1 minus 2x squared. And this is supposed to equal 0. Zero product property says that a function equals 0 when the first factor equals 0 or when the second factor equals 0. An exponential function cannot equal 0, so that's not even an option. My only solution is going to be when 1 minus 2x squared is equal to 0. That's going to give me 1 equals 2x squared, so x squared is equal to 1/2. X is going to be the positive negative square root of 1/2, which you could call the square root of 2 over 2 if you prefer. That's the same thing. Be 0.707. So, and in fact, I'm going to put that just to help me think about it. So I would say, okay, what I would need to set up, these are my critical points. The first derivative test tells me the only place where this function changes from increasing to decreasing is at a negative 0.707, or, well, I'm going to keep it precise, and I'll call it the negative square root of 2 over 2, same thing, and the positive square root of 2 over 2. Those are my two critical points. Now, you could go in and start choosing test points in between these. That's Calc 1. I'll go ahead and say, is there an easier way just thinking about it? Well, yes. We already know this function is always positive. And I say, this is a negative parabola. So the fact that this is a negative parabola means it's going to look like that. I am certain it's going to look like that. Oh, that's horrible. But now, to make a long story short, and again, if you want to go in and choose your test points, that's fine. I'm just not showing that because that's stuff we've already done in Calc 1. So I can say, okay, I know that my first derivative is negative for any value to the right of the square root of 2 over 2. Thus, for all x values, above 1 is what I'm interested in. Yes, technically I could say above the square root of 2 over 2, but square root of 2 over 2 is below 1, so I can certainly say for all x values above 1, f of x is decreasing. Or I'll just say f of x decreases. Now I know it seems like quite a bit of work to do just to set up a problem to work. It does. Now, I finally do the problem. I can say, okay, so that's just given me the permission to take the integral from 1 to infinity of x e to the negative x squared and allow this answer to represent what happens in my series. So I can say, okay, now this integral, that's technically improper notation from 1 to infinity, so I'll make it proper. I'll say this equals the limit as, you can pick any variable you want. I'll pick b, since it's the second coordinate. 1 to b of x e to the negative x squared. Go ahead. So, how would you evaluate this integral? What technique? You see a exponent negative x squared, term down here, looks like it's a multiple of a derivative. Substitution. I'll say, let u equal negative x squared du would equal negative 2x dx. So what I'm going to do here, instead of worrying about changing my limits of integration, I'm just going to come down here and say this integral without the limits of x e to the negative x squared dx would equal, I would need to multiply by negative 2 on the inside, which means the outside would be multiplied by negative 1/2. And then on the inside, it just becomes e to the u du. That I can integrate and say, well, that's going to equal, the integral of e to the u is e to the u. So I'll get negative 1/2 e to the u, technically plus c, but I don't really have to worry about the plus c because I know in the next step I'll be putting this in a definite interval. Now I come back down here and I'll say, okay, so my integral from 1 to infinity of x e to the negative x squared dx is equal to the limit as b approaches infinity of my answer here with x back in the place of u. So negative 1/2 e to the negative x squared and this is evaluated from 1 to b. Say, okay. I'm going to actually switch this around, guys. I'm going to do this. Plus, make this b and make this 1. Okay. So I decided to change my limits of integration. You could show that out in another step. I just decided to change my limits of integration by changing the sign on the inside. So I think make it a bit easier. So I'll have, when I plug a 1 in, I don't have to worry about the limit as b approaches infinity. My limit of integration is 1. So I'll just say, when I plug a 1 in, I'll get 1/2 e to the negative 1. That'll be 1/2 e to the negative 1 is going to be 1 over 2e. Because e to the negative 1 means e to the first belongs in the denominator. From that, I need to subtract minus the limit as b approaches infinity. I need that in here since I know this term's going to have a b in it. And I'll say, well, this is going to be 1/2 e to the negative b squared. So I'll say, okay, that's going to be 1 over 2. And I'm going ahead, again, putting the e in the denominator to get rid of that negative exponent. And then it's just becoming b squared. Instead of a negative b squared, it's a b squared. But I think you can see that this last term is just going to be 0 because if you have 1 divided by 2 times e to the infinity squared, that's 1 over infinity, which makes that whole term 0. The limiting value here is just 1 over 2e. Now, here's the downside of this. People want to say, oh, okay, so the sum of your series is 1 over 2e then, isn't it? No. We have not found the sum of the series. We found the area under the integral of the curve. And the fact that this integral had a finite answer, all that means is that my series would have a finite answer too. My series converges. I have no clue what it converges to, though. So we've done all this just to say, so by the integral test, the series from, 1 to infinity of n e to the negative n squared converges. That would be your
test.
Say that again?
Is that going to be on the test?
But we're going to be doing another practice problem with it on Monday. You're like,
Did we really just go? Sorry,
surely not.
We started this.
One more test today, and you'll like this one. I think I may have said that before and been wrong.
Yeah, probably.
The clock's running slow.
Is this one I'm taking entire page of notes too, or should I just go ahead and flip?
No, I said you'll like this. This is the easiest test there is, the P-series test. And fortunately, it's the easiest, and it's also the most frequently used test. So this is, if you're going to remember any of them, this is the easiest one, and this is the one to remember. So, the P-series test, if I have the summation from n equals 1 to infinity of 1 over n to the p. All that the P-series test it says is that this will converge or converges if p is greater than 1. Sorry, not that equal sign, not there. That's bad, bad, bad. If p is greater than 1, it diverges if p is less than or equal to 1. Just to show you 3 very quick examples of this. What if p is 0.9? You'd say, well, okay, this would be the integral from 1 to infinity of 1 over x to the 0.9 power with respect to x. Now, I'll use the integral test to show that this diverges. So I could say, well, okay, this is going to equal the limit as b approaches infinity, integral from 1 to b of x to the negative 0.9 dx. And then we could say, well, this is going to be the limit as b approaches infinity. When you integrate, you're going to add 1 to that exponent. Negative 0.9 becomes positive 0.1. But if you divide by that 0.1, you're actually multiplying by 10. It's going to be 10x to the 0.1 power from 1 to b. Can you see that this is going to give you an infinite limit? Whenever you plug in the b, you'll have 10 times infinity to the 0.1 power. Yeah, raising infinity to the 0.1 power may decrease it a bit, but it's still infinity. So this is infinity. Which means, and it goes back to up here, if p is less than 1, it diverges. It's because that fraction, yeah, the fraction's getting smaller, but it's not getting small quickly enough. So I'll say, okay, well, what if that's p to the first power down there? And we've actually seen this one before in the notes. I'll say it's the limit as b approaches infinity of 1 to b of 1 over x dx. That's just the natural log of x. And that's going to be evaluated from 1 to b. Well, the natural log of infinity is infinity. So, if p is less than 1, it diverges. If p is equal to 1, it diverges. What if p is greater than 1? I already said this should converge, but I want to use the integral test to show that. I'd say the limit as b approaches infinity of 1 to b, 1 over x to the 1.1 power dx. Well, that's the same thing as x to the negative 1.1 power. Whenever you integrate that, you'll have the limit as b approaches infinity. This is the same thing as x to the negative 1.1. So when I integrate it, it becomes x to the negative 0.1. So I can say x to the negative 1.1 becomes x to the negative 0.1 divided by negative 0.1. I'd rather simplify that up here and say, well, x to the negative 0.1, that's 1 over x to the positive 0.1. And if I'm dividing by negative 0.1, that's the same thing as multiplying by negative 10. I like this format better. Now, you'll see what we're going to do. When I plug in the infinite limit b, negative 10 divided by infinity, 0. Minus, when I plug in the 1, it'll be negative 10 over 1. I'm getting 0 plus 10. My answer is 10. Since the integral has a finite solution, that series is convergent. Now, hopefully you're thinking, why in the world would that make any sense? What we're going to do next class is show how that helps us. So you don't have to write this down. Oh, I said next class. Yeah, well, yeah, maybe I can start off with this. You're like, no, you promised before class.
What?
Ooh, infinity almost in the final. So what if I said use the comparison test to show that this series converges? What on earth would you do? The whole point to the p-series test is you're going to compare this to a p-series with p equals 2 because I don't want you to think, oh, a p-series, it only applies if your numerator is 1. No! It applies whenever the difference in the degree in the numerator and denominator is whatever the degree difference is. So if the degree difference is greater than 1, that series will always converge. I can just look at this, it's converging. I know that. Why? The p-series test. I just say the degree difference in numerator and denominator is 2. P-series test 2 says anything p greater than 1 converges. This will also converge. Now, can it get more complicated than that? Yes. But in the simple sense, that's it right there. So next class, we will review and then test on Wednesday.